Welcome to physics online session. This class will discuss line spectrum of hydrogen atom. Okay. So according to Bohr's third postulate, according to Bohr's third postulate, when an electron when an electron make a transition from higher energy state to lower energy state radiation is emitted. This is Bohr's third postulate. Okay, so when electron make a transition from one energy state to another energy state, radiation absorption or emission of radiation takes place. When electron jumps from lower energy state to higher energy state, so it absorbs the radiation. So when electron jumps from higher energy state to lower energy state, radiation or energy is emitted from the atom. Okay, so let us consider uh, here the electron is making a transition from energy state En to okay, 1 minute. Okay, making a transition from energy state En to N2 energy state to En2 energy state to En1 energy state or simply E1 state. Okay, right. So uh, according to Bohr's third postulate, the energy of radiation, radiation of emitted, uh, the energy of emitted radiation is equals to En2 minus En1 equals to h nu. Okay, this is energy of emitted radiation is equals to h nu. Okay, and we know that from Bohr's theory of hydrogen atom, the energy of electron in the nth orbit is given by E is equals to energy of electron of hydrogen atom. Okay, is given by me power 4 minus me power 4 by 8 epsilon naught square n square h square. Okay, generally z square me power 4 by 8 epsilon naught square n square h square, but for a hydrogen atom uh, z equals to 1. So better to write that one also. So here actual expression is minus z square me power 4 by for hydrogen atom z equals to 1. So we'll get the energy of electron in nth orbit of hydrogen atom is given by minus me power 4 whole divided by 8 epsilon naught square n square h square. Okay, right. En1 is equals to En1 is equals to minus energy of electron in nth orbit can be represented as minus me power 4 divided by 8 epsilon naught square n1 square h square. Energy of electron in second orbit is given by minus me power 4 whole divided by 8 epsilon naught square n2 square h square. Okay, so right now here let it be equation number 1 and let it be these two combinedly equation number. Okay, from 1 from 1 equation number 1 I want to write an expression for frequency nu is equals to en2 minus en1 divided by h, that is equals to 1 by h into by substituting the values of en2 and en1 from equation number 2, we get en2. What is en2? Minus me power 4 whole divided by 8 epsilon naught square n2 square h square minus, and what is en1? Minus me power 4 divided by 8 epsilon naught square n1 square h square bracket, and that implies frequency mu can be written as mu is equals to I'm taking me power 4 by 8 epsilon naught square h square common. So what do you get? So me power 4 whole divided by 8 epsilon naught square h square, already have one h is there, h cube. Okay, and you take this one common from this expression, you get minus 1 by n2 square minus minus into minus plus 1 by n1 square. Okay, right. And we know that frequency in terms of wavelength is given when mu is equals to c by lambda. Okay, so I want to substitute that value in the above equation. We'll get c by lambda is equals to me power 4 by 8 epsilon naught square h cube. We can rewrite this expression as, first I'll write the positive term 1 by n1 square minus 1 by n2 square. Okay, doing the cross multiplication, we get c by lambda is equals to me power 4 whole, sorry, uh, I want to remove this c1. I'm doing cross multiplication so that we get only 1 by lambda on the LHS side. 1 by lambda is equals to me power 4 whole divided by 8 epsilon naught square h cube c to 1 by n1 square minus 1 by n2 square. Okay, right. So this can also be written as 1 by lambda is equals to r into 1 by n1 square minus 1 by n2 square. Okay, so where r is called where r equals to me power 4 whole divided by 8 epsilon naught square h cube c is the Rydberg constant, is the Rydberg constant, the Rydberg constant. Okay, so and its value is given by, value is given by r is equals to 1.097 into 10 power 7 per meter. Okay, after substituting the known value, m is the mass of electron, charge of electron, permittivity value, and Planck's constant, and speed of light, we get the Rydberg constant as 1.097 into 10 power 7. I'll write the known values: mass of electron 9.1 into 10 power of minus 31 kg, and charge of electron 1.6 into 10 power of minus 19 coulombs, and Planck's constant 6.63 into 10 power of minus 34 joule second, and the epsilon naught value is 8.85 into 10 power of minus 12 coulomb square per Newton meter square, and the c speed of light c equals to 3 into 10 power of 8 meter per second. After substituting all the known values, we get the Rydberg constant, so as 1.097 into 10 power 7 per meter. Okay, so this is expression for wavelength. By using this expression, we can find the wavelength of any spectral line. Okay, so hydrogen atom, generally hydrogen atom has 5 spectral series. Okay, so here your hydrogen hydrogen atom has five spectral series. Spectral series. Okay. They are first one Lyman Lyman series. Second one is Balmer series. Third one third one is Passion series. Fourth one Bracket series. Bracket series. And fifth one Fund series. Okay, these are the four series discovered by Lyman, Balmer, Passion, Bracket, and Fun, etc. Now we'll discuss one by one uh, the series. When you will get Lyman series. Okay, first series is Lyman series. When we get Lyman series, when electron make a transition from higher energy states to higher higher energy states higher energy states to ground state ground state or first orbit or first orbit. Okay, we get Lyman series. We get Lyman series. Okay, so and we can find the wavelength of each spectral line by using the above expression. So we know that 1 by lambda is equals to wavelength of each spectral line is given 1 by lambda is equals to r into 1 by n1 square minus 1 by n2 square. Okay, so where sorry, for Lyman series, for Lyman series, here n1 is equals to 1. Okay, so electrons are de-exciting to ground state. They are coming from excited state to ground state. Electron may come from n equals to 2 state to 1 state, or 3 state to 1 state, or 4 state to 1 state. So they are de-exciting from different energy levels to ground state. So that is why N2 may be 2 or 2 comma 3 comma 4 and so on. Okay, so infinity. Right. Now this Lyman series, if you find the wavelength of spectral lines, okay, by substituting the values n equals to 1, by putting n equals to 1, when you put n equals to 2, you will get different wavelengths of different spectral lines, and the series of spectral lines is known as the orderly arrangement of all the spectral lines is known as series, and the Lyman, that series called Lyman series. And in this Lyman series falls in a visible region. Lyman series falls in UV, ultraviolet region. Ultraviolet region. Okay. So if you observe the wavelength of this wavelength of a line in a spectral series of Lyman, so we'll get uh, that wavelength will be in the UV region, ultraviolet region. Okay. You can see the figure here. Uh, you can see this figure. Okay. Right. Here electron is making a transition, electron is making a transition from uh, equals to 2 state to 1 state, or 3 to ground state. Okay, electron comes from second to first, third to first, fourth, fifth, sixth, and so on. So you will get Lyman series. Lyman series is obtained when electron jumps from higher energy state to ground state. Okay, and Lyman series falls in the UV or ultraviolet region. Okay, similarly, I'll discuss remaining here only. When electron jumps from higher energy states to second orbit. Okay, electron jumps from higher energy state to second orbit, we'll get Balmer series. For Balmer series, this is general expression of wavelength is, uh, so I will write that one here. So okay, for Balmer series, for Balmer series, the Balmer series is obtained when electron jumps from higher energy state to higher energy states to second orbit. Second orbit. So we'll get the Balmer series. Okay. So for Balmer series, for Balmer series, this N1 is equals to 2 because electrons are exciting to second orbit. N2 is equals to, they are coming from third, fourth, fifth, and so on infinity. Okay, and this Balmer series falls in the in visible region. Balmer series, Balmer series falls in the visible visible region. Okay, you can see the wavelengths, light emitted from hydrogen atom. Okay, and electrons are de-exciting from higher energy state to second orbit. Okay, and actually it is better to write 1 square. Okay, therefore 1 by lambda is equals to r into 1 by 1 square minus 1 by n2 square. Okay, and for Balmer series it is 1 by lambda is equals to r into 1 by 2 square minus 1 by n2 square. Okay, right. Next, mm, third one, third one, Limer, Balmer, and Passion series. This Passion series is obtained when electron make a transition from higher energy states to higher energy states to uh, third orbit. Higher energy state to third orbit. Okay, and for Balmer series, sorry, and for Passion series, Passion series. So n1 equals to 3. Why? Because electrons are de-exciting to third orbit and they are coming from either n equals to 4, 5, 6, and so on. Okay, and this and the expression for wavelength of each spectral line can be obtained by using this relation 1 by lambda equals to r into 1 by 3 square minus 1 by n2 square. Okay, so where n2 is equals to 4, 5, 6, and so on. Okay, already I wrote it in the previous step. Okay, and this passion series, this passion series falls in the near infrared region, near infrared infrared region. Lyman series falls in the ultraviolet region, and Balmer series falls in the visible region. I will identify here. This Lyman series falls in the ultraviolet region, and Balmer series falls in the visible region. Sorry, visible region, and Passion series, this Passion series falls in the near infrared region. Okay, next series and of hydrogen atom is bracket bracket series. Bracket series is obtained when electron make a transition from higher energy states to higher energy states to fourth orbit, higher energy state to fourth orbit. Okay, and for bracket series, and for bracket series, so n1 is equals to 4. Why? Because they are de-exciting to fourth orbit and they are coming from either 5, 6, or 7, and so on infinity. And expression for wavelength of each spectral line can be obtained by using this relation 1 by lambda is equals to r into 1 by 4 square minus 1 by n2 square, where n2 is equals to 5, 6, 7, and so on up to infinity. And this bracket series falls in infrared also in the infrared region. Bracket series falls in the middle infrared region. Simply infrared region. This is the fourth series of hydrogen atom. Last series of hydrogen atom is Passion series. Sorry, I said wrong. So Passion series are already over. Fund series. Last series of hydrogen atom is Fund series. This Fund series is obtained when electron make a transition from higher higher energy states to the fifth orbit, then we'll get uh, a fund series. For uh, fund series, so electrons are de-exciting to n equals to 5 states, so n1 equals to 5. They are coming from excited states like 6, 7, 8, and so on up to infinity. And the wavelength of each spectral line of a fund series can be obtained by using this relation: 1 by 5 square minus 1 by n2 square, where n2 is equals to 6, 7, 8, and so on up to infinity. And this fund series falls in far infrared region. Fund series falls falls in far infrared region. Far infrared region. Okay. So once again, this is far infrared, and passion near infrared. Last three series bracket sorry passion bracket and fund series. These three series falls in the infrared region. Gamma series falls in the visible region. Lyman series falls in the UV region. You can easily understand with okay. Next okay, okay. Here we can see the different spectral series of hydrogen atom. uh, when electrons are making a transition from higher energy state to ground state, the Lyman series is obtained. It falls in the UV region. When electrons making a transition from higher energy states to second orbit, we get a Balmer series which falls in the visible region. And when electron makes a transition from uh, higher energy state to third orbit, we'll get a Passion series. It falls in the near infrared region, NIR, near infrared region. And when electron making a transition from higher energy state to the fourth orbit, will get bracket series. It also falls in IR region, infrared region. So when electron make a transition from higher energy state to fifth orbit, we will get a fund series. It is not mentioned in the figure. Okay. So this is about the line spectrum of hydrogen atoms, or spectral series of hydrogen atom. Okay. And the next and last topic of this chapter is uh, de Broglie's explanation of Bohr's second postulate. Okay. So I will go to the actual page. Okay, here. mm, okay, so I'll explain. This is the last and the final topic of this chapter. That is de Broglie's de Broglie's explanation of explanation of Bohr's Bohr's second postulate. Second postulate of quantization. Second postulate of quantization. Okay, this is the last and final topic of this chapter. Okay, so here de Broglie explained sorry De Broglie this Bohr's second postulate, explained Bohr's second postulate by assigning assigning wave nature wave nature to revolving revolving electron. Okay, so hmm, actually, according to Bohr's model, electron revolves in a circular orbit. So, whenever according to de Broglie concept, he applied de Broglie's hypothesis to the revolving electron. Okay, so and he successfully explained the Bohr's second postulate. Okay, so according to de Broglie, electron revolves in a circular orbit, and as long as electron revolves in a circular orbit, it does not radiate any energy. Okay, so let us take a nucleus. This is a D of charge D, and electron is revolving in a circular orbit. So this is electron. So uh, here de Broglie assigned a wave nature to electron. So moving particle is associated with a wave that is called a de Broglie wave. Okay, any particle in motion, according to de Broglie's hypothesis, a material particle in motion, according to de Broglie's hypothesis, de Broglie's hypothesis, a material particle in motion, a material particle in motion is associated with a wave known as de Broglie or matter wave, de Broglie or de Broglie wave or matter wave, and the wavelength of de Broglie wave or matter wave is given by de Broglie wave is given by the expression lambda is equals to h by p, where p is a momentum. So momentum is product of mass and velocity, where m is a mass of electron and it is revolving with a linear velocity. V is the velocity of the electron. So we can write this expression as lambda is equals to h by mv. This is another expression. It will be equation number 1. Okay, so right, right. So here the wave. So here he assigned wave nature to electron. So what type of wave is associated with electron? Is it a progressive wave or stationary wave? According to de Broglie, the wave associated with according to de Broglie, according to de Broglie, the wave, the wave associated, the wave associated with the electron, associated with the electron is not a progressive wave, but it is a stationary or stationary or standing wave. Okay, so that is why as long as electron in the that orbit, it does not radiate energy. Why? Because the stationary waves do not radiate energy. Okay, so they do not propagate energy, so they carry energy with it. Okay, that is why the explanation why the electron is not radiating energy when it is rotated in one particular orbit is given explained by de Broglie. Since the wave associated with the electron is standing waves cannot radiate energy. They do not lose energy. They do not radiate energy. Okay, they do not transport energy. Okay, that is why as long as electron revolves in the stationary orbit, it does not radiate any energy. Okay, so here, according to de Broglie, uh, so all the electrons in a allowed orbit, electrons in an in an allowed orbit have have integral multiple of wavelengths, integral multiple of integral multiple of wavelengths. Okay, so that is mm, and we can write it as, and that is equals to, and the, according to de Broglie, and the circumference, sorry, I wrote wrong. So here is circumference of a circular orbit, circumference of the orbit is equal to the integral integral multiple of wavelength. Okay, so that is 2 pi r n. So radius of r, if rn is the radius of nth orbit, its circumference is given by 2 pi rn, that is equals to n lambda. So this is according to de Broglie. Okay, so circumference is equals to integral multiple of wavelength. So where n is equals to 1 comma 2 comma 3 and so on. Okay, so here we can substitute the value of de Broglie wavelength, and into lambda is h by mv from the equation number 1, let it be equation number 2. From equations 1 and 2 we can write, from equations 1 and 2, so this is equation number 1, and equation number 2 we can write 2 pi r n equals to nh by mv, and we can rewrite this expression as mvrn is equals to nh by 2 pi. So this is the uh, Bohr's this is a Bohr's second postulate. Okay, so in this way Broglie successfully explained the concept of explain the second postulate of Bohr. Okay, so how he explained. So de Broglie assigned wave nature to revolving electron. And wave nature nothing but according to de Broglie, when a material particle in motion associated with a wave, that is called a de Broglie wave, and the wavelength of the de Broglie wave is given by lambda is equals to h by p or h by mv. So according to de Broglie concept, wave associated with electron is not the progressive wave, it is a stationary wave. When it is a stationary wave, it does not radiate any energy. We have discussed in the waves chapter. The stationary waves do not carry energy, okay, with it, do not radiate, do not transport energy. Okay, so just the energy uh, confined with the stationary wave. Okay, so according, and also the next point regarding de Broglie electrons in an allowed orbit, here electron can have integral multiple of wavelengths. So the meaning of that sentence is circumference of that orbit is equals to integral multiple of wavelengths. In mathematical form we can write it as 2 pi r n is equals to n lambda, n equals to 1 comma 2 comma 3. So by substituting the value of lambda from the previous expression, equation number 1, will and simplifying, you will get expression that is mvr equals to nh by 2 pi, that is a Bohr's second postulate. So de Broglie successfully explained the concept of Bohr's second postulate by assigning wave nature to electron. Okay, so this is about uh, the atoms chapter. Okay, now I will show one figure here so that you can easily understand the wave nature associated with the electron. Okay, so you can see according to uh, Bohr, electron revolves only in the circular orbit. It is a circular orbit. Okay, And but according to de Broglie, so electron, the waves associated with electron are stationary or standing waves. Okay. For example, uh, you can see that I'll show the next figure here. Okay, look at the first circle. Okay, so a circular orbit. This is the nucleus. Sorry, this is the nucleus, and around the nucleus, electron revolves in first circular orbit. Okay, okay, right. No, according to, so this is the electron revolving in the circular orbit. So the wave nature associated with it will be like this. Okay, so the standing wave associated with electron is like this. So for the second orbit, the wave associated with electron is given by uh, so this is the wave associated with electron. So and when for the first orbit there is only one crust and one trough. For the second orbit, two crust and uh, uh, two crusts and two troughs. So that is it has two wavelengths. Two wavelengths. It has only one wavelength, one wave associated with, two waves associated with. Here and for n equals to third orbit, there are three crusts and three troughs. Okay, so three waves associated with it. Okay, now according to uh, according to Bohr, electron can only present only on the circle. Okay, dotted lines represent the circular as Bohr orbits. Here, this uh, according to Bohr, electron can reside only on the circle. Okay, here electron can reside only on the circle, but according to de Broglie, electron uh, can present anywhere within the shaded region. Electron can be found within any region, here and here. Why? Because it is having wave nature. So so it can present, electron can present in anywhere in this shaded region. Okay, why? Because it has a wave nature. Okay, this is for third orbit, and for second orbit, here it's here in the shaded region, electron can present in anywhere in the shaded uh, area. Okay, so this is about the standing or standing waves associated with the electron. Okay, when it is in the first orbit, it has only one crust. So when it is second orbit, it is like this. Okay, so these are the stationary waves associated with explanation. This is explanation of de Broglie's explanation of Bohr's second postulate. Okay, so up to this we have completed the atoms chapter.